Thank you for inviting me here. I'd like to share with you some recent results on acoustic wave generation. Doctors Norton and Bobuke were talking about two different types of waves, optical waves in the case of microscopy and gravitational waves. And I'll be talking about a different type of medium in which waves can propagate, a material medium, and that would be, we would call that sound waves. But I'm specifically talking about high frequency sound, which is well beyond what the ear would detect. So ultrasound in hospitals, maybe megahertz for imaging, generating a million times higher frequencies in the science building over here. So I presented some results here recently at a couple of conferences, Phonon's 2010 and Laser Ultrasonics, and I've got these collaborators that help provide the samples. Okay, the idea is pretty simple. If you have electric field from a laser, if it's incident on a special type of alternating sequence that's grown by molecular beam epitaxy, so you have alternating layers of positive and negative space charge, then you can exert equal and opposite forces, either up and down or longitudinal in opposition on those opposite charges, because the electric field exerts forces on charges. Okay, and then that wave would propagate through the substrate, and that's the idea, okay? Now there are some, this is a schematic of the experimental arrangement. Everything is immersed in liquid helium here. It's because I got to suppress thermal vibrations from being a noise factor. And I've got a focused laser. I'll show you a picture of that in a few minutes. A sample here to give you an idea of the spatial extent. It's 5 by 7 millimeters, half millimeter thick. It's a silicon start wafer. On the front face, there's a metal structure called a diffraction grating, and on the back face is a superconducting detector. It's called a bolometer, and it just looks at very minute temperature fluctuations from the incoming energy associated with the phonon pulse. These are pistons. I can squeeze that sample and do a type of spectroscopy related to the amount of stress that's applied. And then this is a schematic showing the equal and opposite forces on the different sheet charges, and you get the phonons coming out. The period here is about 34 nanometers. Okay? If you decrease the period by growing a different superlattice, if you excite it with a higher frequency light source, you could get a higher frequency acoustic wave. And that would be advantageous for some applications. Okay, here's a simulation using COMSOL, which is some software that Jack provided. And it really neatly allows you to solve coupled partial differential equations with various types of boundary conditions. This is actually a pretty short movie. It corresponds to about a nanosecond in real time. So this is the superlattice. You don't see it, but there's electric field coming from the light, exerting forces, and that wave is propagating towards the substrate. This is 2 microns in real space. Okay? It's just a small slice. Now, I don't detect waves. I detect the energy from the waves because my detector is not fast enough to respond to the field at 250 gigahertz. Okay, now you've got a wave equation here. Zeta is the displacement from equilibrium. Force is from the electric field. This corresponds to positive and negative sheet charge densities. And you can solve this using Fourier transform techniques. And you get the acoustic intensity as a function of material properties, including the density of dopants in your sheet charge, the mass density, speed of sound, different parameters. Okay. If you calculate the electromagnetic power per unit area per unit time, you get this relationship. This is a dielectric constant, and this is electric field intensity, speed of light. You take the ratio of the acoustic power to the electromagnetic power, and that's the conversion efficiency for the process. And if you put in the material numbers, my samples have 30 layers. That's the dopant concentration, 2-dimensional dopant concentration. That's the period. It's a pretty puny conversion efficiency, right? 10 to the minus 8. Now, I've got 10 kilowatts of far-infrared laser power. I'm only going to get a few nanowatts of acoustic power. So I need a very sensitive detector. That's where the superconducting bolometer enters the picture. Now, there are some considerable constraints on doing this experiment. It took about 20 years or so since anybody's done this, because I think you need some pretty novel tools to accomplish it and see a signal that's not washed out by the much more intense laser light. Okay, so you do need an intense nanosecond pulse far-infrared laser. You need a fast detector. It's critical that you have this metal film on the front face called a grating coupler. There's two reasons for that. I want to produce a compressional wave versus a shear wave, because you can propagate compressional waves in the liquids if you want to do acoustic microscopy at a future date. Shear waves don't propagate in liquids. Secondly, I've got to protect my detector, which can measure nanowatts from the kilowatt laser, because it'll just blow the detector apart. I mean, electrically, it'll just malfunction. Okay, and then also, because I've got this intense laser light, I needed a jig to do some things. I needed to protect it from the laser electrical discharge that's going on in the background. So that was a pretty key improvement. The super lattices, I've got 30 layers, 17.5 nanometers per charge sequence, and it goes positive and negative, and you get about 35 nanometers for the super lattice. These are grown on 6-inch wafers over in University of Stuttgart at the Semiconductor Engineering Institute. Okay, here's some pictures of my laser. It's a custom Terahertz laser. It's pumped by a CO2 laser, so I've got running gases mixed in a manifold. This is about 35,000 volts in an atmospheric discharge of CO2, nitrogen, and helium. The output from that gets focused into, I don't know if you can, probably can't see it that well with the lights on, but this is a custom far-infrared laser. It's about 3 feet long. It's got 4-inch mirrors inside with a coupling hole, and it holds isotopic methyl fluoride, which is carbon-13 with CH3F, and it's pretty expensive, so I recycle it back and forth with cryopumping techniques, and so it lasts for a long time. I can just pump it back and forth. Okay, so the output from that, it's invisible. Lasers in the terahertz frequency, our eyes don't see it. How do you know where it is? I've got it directed about 10 feet in my lab down to the liquid helium cryostat, which holds a sample. So fortunately at MIT in their plasma fusion facility, they developed some corrugated waveguides, and they snap together. And that was a beautiful solution to my problem. I didn't have to design these myself. And so they just snap together, and I run it down, and it comes in, and it'll get focused into the entrance window where the sample is, okay? Now, I get pulses. I've got a piece of silicon. This is my far-infrared laser. The CO2 laser comes in through a hole here. This is the beam profile of the far-infrared laser radiation. I've got a silicon wafer sitting at the Brewster angle. That baby is normally transparent. It's just as if the far-infrared light doesn't even see it. It goes right through it at the Brewster angle. It's very pure crystal. However, if you zap it with frequency doubled YAG light, just like this green, this is YAG, it'll turn this into a metal type surface layer called a plasma, electron hole plasma. It becomes metallic, it becomes mirror-like. You can turn that on in a nanosecond time scale, and once that's turned on, now you've got a mirror sitting inside your cavity, and any energy making a round trip is going to see that mirror and come out and get captured and go down into that corrugated waveguide for beam transport. Okay, here's a pulse in the chartreuse, I guess here. It's about 5 nanoseconds. This broader pulse is the green YAG laser that causes the cavity dumping. So I get 5 nanosecond pulses. I'm getting about 10 kilowatts. There's not a big demand for systems like this, so you just can't go out and buy one. You have to build these things. It takes a little time. Okay, I think I'll skip over this, but this is the grating coupler. You can design the period. It's basically a series. I'll show a picture. There's some metal line spaces. If you choose the period of that geometry correctly, you can control how deep the electric field penetrates underneath the grating. And I want it to penetrate into the superlattice. Here's a picture of the grating. I make these over at WV Nano in Morgantown in the clean room. And this is the grating. It's niobium. Niobium is superconducting at about 9 degrees Kelvin. And its gap energy is 680 gigahertz. I'm producing 250 gigahertz. So the 250 gigahertz photons from the far-infrared laser, they don't produce any absorption in the niobium for physics reasons. Okay. However, if I want to go up to terahertz, I got to change from niobium to niobium titanium nitride. Sounds easy, but now I got to go out to Jet Propulsion Lab and have some people help me do that, because it's a very custom way of growing these films. The bolometer here is, this is just aluminum covered with a little palladium. These are the contact pads. I've got two different size bolometers. This is about a half a millimeter. It's not that small. And this is 10 by 20 microns, the active area in between the contact pads. Okay, so that's been fun, going to Morgantown, taking a suitcase with my samples in there. And I do this, stay a week, and if I'm lucky, after a week I got samples. Okay, I'll skip that. That's the stress. I'm not doing that yet. There's a stress apparatus. My sample's in here. I have this jig that was critical. I've got a silicon lens that focuses the far-infrared laser light onto the sample, which is right here. That's the sample. The lens is in contact with it. This is a polymer. You can draw this in AutoCAD. You can send it out to a company called Rapid Prototyping, and they'll drop your FedEx jig or piece in the mail the next day. And this is my coaxial cable connector for the contacts. This is metal coated. It's beryllium coated, so it's like a Faraday cage. It eliminates the laser discharges going on in the room, the noise. Okay, now the bolometer needs to be characterized, so you need to know certain things about it, so you know if you see a signal what power is being detected. And I can skip over that, but you can, this is the resistance versus temperature. This is only 1/10 of a Kelvin. So this bolometer's got a transition. It's pretty narrow. It's about 1/10 of a Kelvin. And the resistance is around 10 ohms, 10 to 0 ohms. The slope of that's called the sensitivity. You can also measure the resistance for different currents at different temperatures, and you get a set of data like this. You can curve fit some of that data, and you can, lo and behold, you can extract the parameters that tell you the performance of your bolometer. Okay. And I get about 10 kilovolts per watt. So I can, with 2 nanowatts of phonon power, I should see an 18 microvolt signal unamplified. This is what I measure. I've time averaged here, actually. I've averaged maybe, I think it was 4,000 pulses. My laser's pulsed, like pop, 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 10 times per second, 5 nanosecond pulses. So if you average here, now, this big pulse, that's leakage through that niobium grating coupler. The far-infrared laser does penetrate. The grating coupler is about I think it's 500 nanometers thick. I need to make it thicker. However, it's a nice benchmark. The phonon signal is actually that little bump right there. Okay, now phonon physics is pretty notorious for getting an easily detectable signal. So I was pretty happy to see that's easily discernible. I'm using a small detector right now. I can use a larger one and I'll get a signal that should be 200 times bigger. However, currently I'm out of money. I've got to wait for more funding to come in so I can go over to Morgantown and pay the clean room fees, or maybe Jet Propulsion Lab. This is actually, this is leakage coming through. This pulse is when that YAG laser pulse causes the cavity dumping. This is the large cavity dumping pulse. It's not to scale in the sense that this, my detector is saturated. It would be much bigger. It's saturated, okay. But that's the phonon signal. So it's the first time anyone's ever demonstrated coherent acoustic phonon terahertz generation. Now, it's a new type of probe. You've got a wave. You've got quanta of energy associated with that wave, like you have photons associated with optical waves. You got an acoustic probe, like ultrasound imaging in hospitals. What are some applications? Okay, one application is that's pending in a couple of proposals is to use phonons to scatter off defects in the wall materials of Hall thrusters that are used by NASA for space propulsion, non-chemical space propulsion. And here's a picture from NASA Glenn Research Center. You got Xeon ions coming out. That gives you the kick in the opposite, you get an impulse the other way. So it's a rocket. It's a non-chemical rocket. And right now, it's Hall thrusters, electrostatic thrusters, cross field. They have electric and magnetic fields. And the electric field is accelerating these charges out the back end. There's not much mass. But if you wait long enough, you'll get a large enough change in velocity from a small acceleration. They don't know, these things do fail, but they don't have any clear-cut physics modeling yet for the failure mechanism and being able to predict the lifetimes of these. What's failing? The wall material is being eroded from that ion beam, okay? So from NASA, in their roadmap of what they consider technical challenges, there's a new BAA that came out called Game-Changing Technology. So I'm submitting a proposal to where we propose to use the phonons for modeling, physics-based model of the plasma erosion process. Okay, now what's that going to do? The effort here, I'm going to change my phonon source from 1/4 terahertz to 1 terahertz. I can get thinner superlattices, fine. I got to go to this niobium titanium nitride so I don't get absorption, fine. Where do I get the wall materials? By some small miracle, from my perspective anyway, there's a guy at Rice that can grow hexagonal boron nitride, 2D films, same material they use in the Hall thruster walls. He can grow them, thin layers, and transfer them directly onto my silicon substrates, okay? That's, without doing that, I couldn't do this work that we're proposing. Then we would take those samples and take them up to Glenn Research Center, put them in those plasma plumes, and for different exposure times, bring them back here, measure the transmission of the phonon pulses through those layers that will have been exposed to the plumes, which will have induced defects into the defects. No, did I say that twice? I think induced defects into the layers. Okay, and then finally, we've got some folks, Dr. Spirot might be involved, hopefully, but there's some other people that are also doing molecular dynamic simulations of the process. Okay. The Rice technique to grow the layers, it's a pretty clever transfer technique. He fabricates hexagonal boron nitride by a gas at high temperature onto copper, okay? Then he applies PMMA on top of that. He etches away the copper, and he's got PMMA and the hexagonal boron nitride. He flips it over, puts it on my silicon substrates, and then he removes the PMMA organic and acetone. And then finally, I just have the wall material on top of my silicon. That's the idea. Okay, now just some quick calculations for the expected scattering rates to see if it might be possible to measure anything after, in terms of transmission. Okay, so there's a scattering rate for acoustic waves in a lattice or a crystal. And it's given by this expression. Nu is the frequency. V naught is the volume per atom of your crystal. That's the speed of sound. G is related to the defect concentration that you might expect, like 20%, 1%, some concentration percentage. D is what's called the density of states, the phonon density of states. And these are just been reported in the last 2 years, and I pulled them out of the literature. So I can calculate the scattering rate. And putting it into the phonon attenuation, if D is the thickness of your layer, which has these defects, tau is the scattering time. It's the inverse of the scattering rate. V is the speed of sound. And if you put these in, I get about 8% for a 10 nanometer thick layer. Okay, so it's just in the ballpark. And I guess I have to wrap up. This is a simulation, molecular dynamic simulation done by someone else of xenon bombardment onto one of these two-dimensional hexagonal films. Another application, could be higher frequency ultrasound instead of hospitals where you see millimeter structures like you know, baby heart valves and fetuses. You could do semiconductor subsurface imaging. This was done in the 80s at 4 gigahertz with 500 nanometer resolution. If I can increase the frequency to terahertz, I can get down to 1 nanometer resolution for subsurface imaging. So that would be a pretty useful microscopy, although that's going to take at least 10 years because I know the challenges involved in trying to get there. On paper, it should be able to be, it's possible, but experimentally get there, it's another. So I'd like to thank you for listening to me. And so the conclusions, I've got a demonstrated phonon source. It's all in agreement with theory. I got some thanks to my some clean room support staff that taught me the ropes at different places. And these 2 applications are in the pipeline. So, are there any questions?
Any quick questions?
So the phonon interaction is much stronger than the optical, so that's why you're not using like terahertz light, you're using acoustic?
In the scattering of the hexagonal boron nitride?
Yeah.
Okay, this is going to be an incipient erosion process, so it might be very difficult to pull these out and do transmission electron microscopy. So I mean, this is not going to be easy either, but it's an approach nobody's postulated, and the NASA scientist at Glenn is pretty keen on the idea. So it's a new application for me, but other people seem to be interested in it, so I'll bow to their expertise as to why it might be more useful in other diagnostic techniques.